Hello my friends and welcome back to the You Can Do TV channel. Steel is a timeless material essential to the modern world. It provides stability, safety, and enables the transport of raw materials and goods globally. Machinery and equipment rely on steel, and it plays a vital role in environmentally friendly energy production. Today, steel is a high-tech product, and Salzgitter Flachstahl GmbH Zeta is a leading producer. The workflow starts by raw materials, primarily iron ore sourced worldwide, from Scandinavia, Russia, Canada, South America, Africa, and Australia. These raw materials include lumps, fines, and pellets, small spheres of concentrated iron ore that are easy to transport and process. At the Zeta site, several blast furnaces, the largest over 50 meters tall, produce up to 14,000 tons of pig iron daily. Coke, ore, and lime are layered into the furnace, where preheated air generates processed gas at around 2,000 degrees Celsius. This removes oxygen from the iron oxide, melting the iron in an 8-hour process. Liquid iron and slag collect at the furnace base and are tapped approximately every 2 hours at 1,450 degrees Celsius. Where slag separates from the pig iron. The molten pig iron is transferred via torpedo ladles to converters. Zeta operates 3 LD converters where pure oxygen is blown into molten iron, raising the temperature to about 1,700 degrees Celsius and removing impurities through the carbon drop process. This conversion takes about 40 minutes. Producing crude steel. Next, alloying elements like manganese, silicon, chromium, and nickel are added to meet specific customer needs. The steel is then cast into slabs via continuous casting lines, producing slabs up to 35 centimeters thick and weighing as much as 32 tons. Most slabs go to the hot strip mill, where they are heated to around 1,250 degrees Celsius and rolled into wide strips. Hot rolling softens the steel, reducing the forces needed to shape it. The strips are then cut, pickled to remove scale, and cold rolled to thinner gauges in the cold rolling mill. Final surface treatments include skin passing, electro-zinc coating, and hot-dip galvanizing for corrosion resistance. Zeta's products serve diverse industries, including construction, automotive, energy, and special machinery. The company maintains an extensive product warehouse and a global sales network. Energy efficiency is a priority at Zeta. The steel plant operates its own power station, recycling gases from production to generate steam and electricity. Research and development remain key to innovation. Collaborating with universities and customers, Zeta focuses on optimizing products and processes, ensuring steel remains a vital, sustainable material. Steel's recyclability and durability make it an ecological choice. Its recycling conserves resources and supports a sustainable future. Steel's role as a fundamental construction material continues both today and into the future. KOG Rolling Glass specializes in producing sheet glass and other glass products. Their furnace, known as the Beehive, can cook 12 colors simultaneously. Inside the furnace are ceramic fire clay pots, called crucibles, each holding about 1,400 pounds of chemicals. There are 12 crucibles in total, one for each color batch. The process begins as molten glass is carefully ladled from the crucibles and brought to the mixing table. Workers deposit the molten glass onto the heavy steel mixing table, where the tableman skillfully blends it using a two-pronged fork until it reaches the desired specification. Once blended, the molten glass is fed between two rollers, similar to rolling pins, which flatten the glass to a thickness of 1/8 inch. The ladles used by employees are very heavy, weighing between 20 to 50 pounds when empty, and potentially doubling in weight when full, so handling them requires strength and precision. To coordinate production, the tableman rings a bell approximately every minute and a half, signaling ladlers to prepare the next sheet of glass. The mixing table is cooled internally by water, and the rollers are hollow and air-cooled to help control the temperature of the glass during rolling. After being flattened, the glass changes direction and enters the annealing layer, where it undergoes a slow, controlled cooling process to relieve internal stresses and ensure durability. This careful, hands-on process ensures high-quality sheet glass suitable for various uses. At Atomash, the bottom of a nuclear reactor for the Akuyu nuclear power plant was successfully stamped. The operation consisted of two stages. First, at Atomash's thermopress section, the forged steel blank, originally in the shape of a pipe, was flattened into a metal sheet under press pressure. The second stage involved drawing the bottom. The circular blank, weighing 64 tons and 300 millimeters thick, underwent a three-stage heating process lasting 6 hours, reaching a maximum temperature of 10-20 degrees Celsius. After heating, the blank was moved by crane into the stamping die, where a press applied a force of 10,000 tons to shape the reactor bottom precisely. Franchini Acciai S.p.A. is a leading European manufacturer specializing in high-quality steel forgings. Established in 1968 and located in Mairano, Brescia, approximately 80 kilometers from Milan, the company has continuously advanced through substantial investments in technology and product diversification to satisfy global market requirements. The manufacturing process begins with a selection of premium ingots sourced from reputable European steel mills. These ingots undergo precise cutting using a combination of 20 saw cutters and an oxy-fuel cutting machine, optimizing the dimensions for forging. Forging represents the core of operations. The facility operates 10 furnaces, each with volumes up to 450 cubic meters, enabling efficient heating of ingots, either from inventory or directly from steel mills via insulated transport trucks. Once heated to the required temperature, The ingots are forged using 3 open die presses with capacities of 2,500, 3,500, and 8,000 tons, equipped with automated manipulators, capable of handling forged components weighing up to 100 tons. The heat treatment department employs advanced technology to impart the necessary mechanical and metallurgical properties to forged parts. Furnaces reach temperatures of up to 1,150 degrees Celsius, and quenching tanks utilize water or polymer media stirred by adjustable propellers to ensure uniform cooling. Heat-treated components can measure up to 24 meters in length, with automated loading systems enhancing process efficiency. CNC-controlled machining centers perform both rough and fine machining using vertical and parallel lathes, milling machines, and drilling equipment. Quality assurance follows ISO 9001-2015 standards, including non-destructive testing methods such as magnetic particle, dye penetrant, and ultrasonic inspections, as well as hardness testing, to ensure compliance with strict specifications. Serving sectors such as oil and gas, energy, naval, nuclear, and petrochemical industries, the company exports approximately 80% of its products worldwide. Continuous innovation and stringent quality control define the organization's commitment to excellence. Sarstall Rail, based in Hayange, manufactures premium quality rails using steel produced with low carbon dioxide emissions at the electric arc furnace in Saint-Sauveur. The production begins with steel blooms transported primarily by rail to the rolling mill. Upon arrival, the blooms are stored and then heated in gas furnaces to the required rolling temperature. The rolling process starts in 2 reversible roughing stands, where the bloom undergoes 8 to 12 passes to form a preliminary rail shape. This is followed by the universal rolling process in 6 stands, where the final rail profile is produced. The last stand also embosses identification marks, in compliance with international standards. After rolling, the rail is cooled on a cooling bed. A controlled horizontal camber is applied to compensate for thermal contraction, ensuring straightness at room temperature. Vertical and horizontal straightening is performed using roller straighteners. Final inspection includes non-destructive testing, dimensional checks, surface quality, and ultrasonic testing for internal flaws. If all criteria are met, rails up to 100 meters long are finished and shipped by rail or truck to clients. The Zuslektovaci Linka Pro Taikovu O-Cell is a heat treatment line designed for bar steel to enhance its mechanical properties and performance. This process typically includes heating, quenching, and tempering stages that refine the steel's microstructure, improving hardness, strength, and toughness. The line can handle various steel grades and bar sizes, ensuring uniform treatment throughout the material. Automation and precise temperature control are key features, allowing for consistent quality and efficient production. The treated bars are used in demanding applications such as automotive components, machinery parts, and construction elements. By optimizing mechanical characteristics, this heat treatment line extends the service life and reliability of steel bars in industrial applications. Steel is an alloy of iron and carbon, often used in machining processes like turning and milling. It includes carbon steel and alloy steel, with historical types like Damascus and Toledo steel. Steel is used in construction, tools, and special applications. Other metals may also be present in its composition. Sand casting is a traditional metal casting process used to create complex metal parts by pouring molten metal into a sand mold. The process begins with creating a pattern, usually made of wood or metal, which forms the cavity in the sand mold. After packing sand around the pattern and removing it, molten metal is poured into the cavity. Once solidified, the mold is broken to retrieve the casting. Sand casting is cost-effective, versatile, and suitable for large components or low-volume production. It's widely used in industries such as automotive, energy, and heavy machinery for producing strong, durable parts. Engine blocks are the heart of modern internal combustion engines. Their strength, precision, and thermal resistance are critical to engine performance. One of the most efficient methods to produce engine cylinder blocks is high-pressure die casting, a technology widely used in the automotive industry for its ability to create complex, high-precision components with excellent surface quality. So what exactly is high-pressure die casting? High-pressure die casting, HPDC, is a metal casting process where molten or semi-solid metal is injected into a steel mold, known as a die, at extremely high pressure and speed. This process enables the production of engine blocks that are both strong and dimensionally accurate. It begins by melting a lightweight metal alloy, commonly aluminum or magnesium, in a furnace. Skimming slag is the process of removing oxide layers and impurities floating on the surface of molten aluminum. This helps purify the metal, improve casting quality, reduce porosity, and ensure the final product's strength and durability. Once the metal reaches the correct temperature, it is transferred into a shot chamber of a die casting machine. The molten metal is then forced into the die cavity using a piston at pressures ranging from 1,500 to over 25,000 psi, pounds per square inch. The high pressure ensures the metal fills even the most intricate parts of the mold before it begins to cool and solidify. This rapid filling and cooling help prevent air bubbles and shrinkage, resulting in a dense and structurally sound casting. After the metal has solidified, the die opens and the newly formed engine block is ejected. The casting will still require additional processes such as trimming excess material, flash, heat treatment to improve mechanical properties, and precision machining for critical surfaces like cylinder bores and bearing seats. The advantage of high-pressure die casting lies in its efficiency and repeatability. It allows manufacturers to produce hundreds of identical engine blocks with minimal variation, while also reducing waste material. Compared to traditional sand casting, HPDC offers faster production times and thinner wall sections, which helps reduce the overall weight of the engine, a key factor in improving fuel efficiency. In conclusion, high-pressure die casting is a crucial technology in modern engine manufacturing. It combines speed, strength, and precision to produce high-quality engine blocks that power vehicles around the world. The spool-based pipeline fabrication process involves a series of highly controlled and precise steps to ensure each pipe joint is welded, tested, and coated to industry standards. It begins with the pipe being rolled into the pipe-facing station. Here, the pipe end is thoroughly cleaned both inside and out. The end is then beveled to prepare it for automatic welding. An inspector checks the offset and land to ensure accuracy before proceeding. The beveled pipe is then transferred to the preheat station. This station performs several critical tasks. First, the pipe end is buffed to provide a good electrical ground for welding. The pipe is also tested for magnetism. Once verified, the pipe ends are fitted with induction coils, which preheat them to the required welding temperature. Then, welding begins when the reach rod is inserted into the upstream pipe. An internal clamp is pulled into place, and the rear shoes are set to hold the pipe in position. The next joint of pipe is moved into place and carefully aligned. The spacer verifies a proper fit by tapping the pipe with a hammer. The clamp's front shoes are then raised to secure both pipe ends together. The P450 CMT cold metal transfer bugs are positioned on the pipe band. After aligning the torch tip, the root pass is deposited using the CMT process. As the root pass is laid down, additional welding stations simultaneously apply their respective passes. Once welding is complete, all weld spatter and silica residue are brushed off to clean the weld. Next, the weld undergoes non-destructive testing. Real-time scan results are displayed immediately to identify any defects. The pipe surface is then cleaned using an abrasive blasting system. Abrasive material is blasted from a nozzle and instantly reclaimed by a powerful vacuum. This process removes oxidation and contaminants, leaving a clean surface ready for coating. Fusion bonded epoxy, FBE, is applied to the weld area. An induction coil is used to heat the weld to the application temperature. The coating head is then placed on the pipe, and a timer begins once it completes its first revolution. A polypropylene coating is applied using an extruder that deposits material over the weld. Radiant heat prepares the factory coating for bonding. A laser aligns the mold over the weld, and the mold is locked into place. Once secure, the mold is filled with molten polypropylene. Excess material is trimmed with a knife while still soft. After trimming, the joint is quenched to solidify the coating, then dressed for final inspection. A polycarbonate shell is attached to the joint to protect it during the cooling phase. This meticulous process ensures the pipeline is durable, corrosion-resistant, and ready for offshore or onshore installation, meeting the highest standards of safety and performance. Egg. Mueller employs skilled tradespeople across multiple technical disciplines, including mechanical fitting, CNC machining, welding, and assembly. The workflow is dynamic, involving tasks ranging from precision machining of components to robotic welding setup and system integration. Operators frequently engage in manufacturing processes such as part fabrication, test fitting, conveyor operation, and fault diagnosis. Typical fabricated components include bearing housings and roller stubs, while structural welding involves conveyor frames and fabricated steel assemblies for client projects. Apprenticeship programs emphasize hands-on technical training combined with theoretical instruction. CNC machining apprentices focus on producing components within strict tolerances for diverse machinery applications, gaining proficiency on lathes, mills, and related CNC equipment. Practical skills are complemented by formal education at TAFE, integrating engineering principles with machining operations. Boilermaker apprentices develop welding competencies through progressive task exposure, including structural fabrication of overhead trusses and architectural steel elements. Learning occurs primarily through direct mentorship and on-the-job training alongside experienced tradespeople. Operational leadership at Mueller exemplifies career progression from technical apprenticeship to management. The operations manager oversees multidisciplinary teams including electrical, mechanical, and software engineering personnel. Project scope spans commercial, industrial, and automation sectors, involving system installations such as robotic storage solutions, factory automation lines, and building infrastructure upgrades. Mueller's technical environment prioritizes skill development, quality workmanship, and continuous process improvement. Apprenticeship pathways provide immediate practical engagement and financial remuneration, offering a viable alternative to university education. The company integrates advanced manufacturing technologies and lean operational methodologies to maintain competitive performance in complex industrial applications. The Gildemeister CTX Gamma 2000 is a high-performance CNC turn mill center designed for precision machining of complex components. It is widely used in industries such as automotive, aerospace, energy, and mold making, where high accuracy and multi-axis machining capabilities are essential. This machine combines turning and milling operations in a single setup, significantly reducing production time and improving efficiency. The CTX Gamma 2000 offers a maximum machining diameter of 700 mm and a maximum machining length of 2000 mm, allowing it to handle large workpieces. It supports bar diameters up to 127 mm. The machine features generous travel distances with 800 mm on the x-axis, 420 mm on the y-axis, and 2050 mm on the z-axis. Its B-axis offers a fine positioning resolution of plus or minus 0.001 degrees, enabling precise angular milling and turning. Equipped with a powerful main spindle rated at 59 kilowatts, it can reach speeds up to 2,000 revolutions per minute and torque of 4,000 Newton-meters. The counter spindle has 40 kilowatts power, speeds up to 4,000 revolutions per minute, and torque of 700 Newton-meters, allowing for efficient machining on both ends of a workpiece. The milling spindle delivers 36 kilowatts with speeds up to 12,000 revolutions per minute, facilitating a wide range of milling operations. The tool magazine can hold 36 tools with options to expand up to 180, enabling flexible machining without frequent tool changes. The machine uses the Siemens 840D control system with shop-turn software, providing an intuitive interface for programming and operation. This control supports advanced functions like direct measuring systems on all axes, with MagnaScale technology, enhancing precision and repeatability, temperature stabilization systems on the X-Y-Z axes, and the main spindle motor ensure consistent machining accuracy during long production runs. The CTX Gamma 2000 is built with automation in mind. It can be integrated with automatic loading and unloading systems, vision measurement tools, and real-time monitoring software for process control and optimization. These features help reduce operator intervention and improve overall productivity. After machining, the rails and tools undergo strict quality control, including dimensional inspections and non-destructive testing to ensure compliance with industry standards. The machine's robust construction and advanced technology provide excellent stability and reliability, even in demanding production environments. In summary, the Gildemeister CTX Gamma 2000 is a versatile and powerful CNC machining center suitable for producing high-precision parts with complex geometries. Its turn mill capabilities, combined with advanced control systems and automation options, make it an excellent choice for industries requiring efficient, accurate, and flexible manufacturing solutions. The FOOKE Endura 704 Linear is a high-performance 5-axis CNC milling machine designed for precise machining of large and complex workpieces. Its compact gantry design allows for travel distances of 2,200 mm in the x-axis, 3,500 mm in the y-axis, and 1,500 mm in the z-axis, making it suitable for handling substantial components. The machine is equipped with water-cooled linear motors on all linear axes, which provide high dynamics and rapid acceleration up to 3.5 meters per square second. It features a high-frequency spindle capable of reaching speeds up to 24,000 revolutions per minute, enabling efficient material removal and excellent surface finish. The 68-position automatic tool changer allows for flexible machining with a wide variety of tools. Robust construction, combined with direct measuring systems and thermal decoupling, ensures consistent accuracy and stability even during long production runs. The FOOKE Endura 704 Linear uses the Heidenhain ITNC 530 HSCI control system, providing advanced programming and user-friendly operation. This machine is ideal for demanding industries such as aerospace, automotive, and mold making, where precision, speed, and reliability are crucial. The automatic aluminium window and door production line is engineered specifically for applications requiring precise 90-degree or 45-degree cuts. Central to this system is the latest generation saw unit, optimized to enhance production throughput while maintaining high accuracy and repeatability. The cutting line features a fully automatic pusher mechanism that feeds aluminium profiles into the cutting zone consistently and efficiently, minimizing manual intervention and cycle time. Coupled with this is a rotating gripper system, which securely holds and positions profiles during the cutting process to ensure exact angles and dimensional integrity. Profile positioning devices are integrated with automatic setup capabilities, allowing rapid adjustments and reducing changeover times between different profile types or cut angles. This automation contributes significantly to minimizing downtime and increasing overall equipment effectiveness, OEE. A multi-spindle system enables simultaneous processing of multiple cuts or profiles, further boosting production capacity. The system is equipped with a 3-blade saw configuration designed to deliver clean, burr-free cuts. Automatic clamps secure the profiles firmly during cutting, preventing vibration or movement that could compromise cut quality. Together, these features create a highly efficient, reliable, and flexible cutting solution tailored for the aluminum window and door manufacturing sector. The line's automated processes reduce operator workload, improve product consistency, and increase throughput, essential factors in meeting the high-volume demands of modern fabrication facilities. This cutting line represents a significant advancement in aluminum profile processing technology, providing manufacturers with enhanced precision, speed, and operational efficiency. In 2016, Global Castings LEM focused on mass-producing high-volume finished castings for the wind energy industry. The company employed advanced casting techniques to manufacture critical components such as turbine hubs, mainframes, and gearbox housings. These parts, designed for durability under harsh environmental conditions, required high precision and consistency to meet the wind energy sector's technical specifications. The production process automated systems to achieve efficient, large-scale output. Sand casting and precision machining were primary methods, ensuring dimensional accuracy and surface quality. The castings, typically made from ductile iron or steel alloys, were engineered to withstand high mechanical loads and fatigue, essential for wind turbine longevity. Quality control involved rigorous testing, including non-destructive methods like ultrasonic and magnetic particle inspections, to detect internal defects. Dimensional verification ensured compliance with tight tolerances required by wind turbine designs. The facility also integrated advanced simulation software for casting design and process optimization, minimizing material waste and production errors. Global Castings LEM's operations in 2016 prioritized technical efficiency, scalability, and adherence to industry standards, supporting the wind energy sector's demand for reliable, high-performance components. UKB Special Tools 2 are high-precision press brake tools specifically designed for sheet metal bending applications. Manufactured in Germany, these tools are known for their exceptional quality, durability, and customizability. UKB offers a wide range of standard and special press brake tools, including punches, dies, and special profiles, tailored to meet the demands of complex bending tasks in modern metal fabrication. In particular, the UKB Special Tools 2 line includes specialized dies and punches that allow users to perform precise and repeatable bends, even on challenging materials or intricate parts. These tools are used in industries such as automotive, aerospace, construction, and general metalworking, where accuracy and efficiency are critical. They are compatible with most press brake machines and can be manufactured in different hardness levels, coatings, or geometries based on customer needs. One of the key advantages of UKB tools is their modular system, which allows for quick tool changes and reduced setup times. Additionally, UKB provides engineering support to help customers select or design the most effective tool for their specific application, ensuring optimal forming results and longer tool life. UKB continues to innovate in the field of press brake tooling, offering solutions that combine German engineering excellence with practical functionality in demanding production environments. Roll forming is a continuous bending process where a metal sheet passes through multiple roll stands, gradually forming a desired profile. It is suitable for high-strength materials and produces consistent shapes with minimal material stress and tool wear. The process is digitally designed and simulated to monitor geometry, forming forces, and residual stresses. Springback is compensated by overbending. Roll forming is used in automotive, construction, and furniture industries, often as part of integrated production lines for efficient, high-volume manufacturing. The automatic Y-shaped aerosol production line is a streamlined and high-speed system designed for efficient spray paint can filling. Its Y-shaped configuration enables parallel processing, improving output and reducing bottlenecks in large-scale aerosol production. The process begins with empty cans entering the line via an automatic conveyor. These cans are directed to the valve insertion station, where a valve feeder accurately places spray valves into each can. A small steel mixing ball is dropped into each empty can. This ball helps mix the paint and propellant during use, ensuring even spray and color consistency. Precision and alignment are critical at this stage to ensure proper sealing later in the process. Next, the cans move to the crimping and gas filling station. Here, the valves are securely crimped onto the cans, creating an airtight seal. Simultaneously, the gas filling nozzle injects the selected propellant, typically LPG or DME, into each can. This is done with high precision to maintain correct internal pressure and product safety. In the parallel branch of the Y-line, the paint filling nozzles dispense the paint formulation into the cans. This includes solvents, pigments, and binding agents. These nozzles are designed for speed and accuracy to ensure consistent fill volumes. After gas and product are filled, cans proceed to the outer cap feeder, where actuator caps are automatically placed and pressed onto the cans. The filled and capped cans are then conveyed to the end of the line as finished products ready for packaging. At this stage, optional leak testing, labeling, and batch coding can be integrated. Equipped with PLC control and safety interlocks, this Y-shaped line ensures smooth operation, minimal waste, and high-quality output, ideal for spray paint manufacturers requiring fast, reliable production. The Deutsore tractor assembly plant is a state-of-the-art facility dedicated to producing high-quality tractors with advanced technical precision. The factory integrates modern automation technologies and skilled craftsmanship to ensure that every tractor meets rigorous performance and safety standards. At the heart of the plant is an automated assembly line where robotic systems handle critical components such as engines, transmissions, and hydraulic units. These automated processes increase efficiency and accuracy, reducing the risk of human error and ensuring consistent quality. Each tractor undergoes comprehensive testing within the facility. This includes engine performance checks, emission testing in compliance with global environmental regulations, and safety inspections. The plant also focuses on calibrating hydraulic systems and transmission settings to ensure smooth operation under various agricultural conditions. The Deutsore 6175 TTV tractor is a powerful and advanced machine designed for modern farming. Equipped with a 6-cylinder, 6.1-liter engine, it delivers 175 horsepower, providing strong performance for heavy-duty tasks. The engine complies with the latest Stage 5 emission standards, ensuring environmentally friendly operation while maintaining fuel efficiency. One of the key features of the 6175 TTV is its continuously variable transmission, TTV, which offers smooth and precise speed control. This technology enhances productivity by allowing the tractor to operate efficiently at any speed without shifting gears manually. The hydraulic system is highly capable, with a lifting capacity of over 9,000 kilograms, making it suitable for a wide range of implements. Overall, the Deutsore 6175 TTV combines power, technology, and comfort, making it an excellent choice for demanding agricultural work. Spirit AeroSystems, a global leader in aerostructure manufacturing, leverages cutting-edge technologies to produce critical aircraft components such as fuselages, wings, and propulsion systems for clients like Boeing and Airbus. Headquartered in Wichita, Kansas, and operating facilities worldwide, Spirit integrates advanced manufacturing techniques, automation, and innovative materials to meet the aerospace industry's demands for precision, efficiency, and sustainability. Spirit's manufacturing prowess is rooted in its adoption of Industry 4.0 technologies, which integrate digital tools, automation, and data-driven processes to enhance production efficiency. A cornerstone of this approach is tact-based production, a lean manufacturing technique that synchronizes assembly processes to a consistent rhythm, minimizing waste and optimizing resource use. In its Wichita facility, Spirit employs takt time for the Boeing 737 fuselage production, ensuring parts and tools are organized for seamless workflow, reducing downtime, and maintaining high output rates. This method is critical for high-volume programs, allowing Spirit to deliver approximately 70% of the 737 structure, including fuselages, pylons, and wing components, with precision and speed. Automation plays a pivotal role in Spirit's manufacturing strategy. The company utilizes advanced robotics to handle repetitive, high-precision tasks, such as drilling and fastening, which are essential for assembling complex aerostructures like the Boeing 787 fuselage and Airbus A220 wings. For instance, Spirit Exact, a proprietary technology, enables toolless assembly by using precise measurements and automated systems, reducing the need for costly fixtures and improving production flexibility. This technology has been instrumental in streamlining the Boeing 737 assembly process. Additionally, Spirit integrates augmented reality, AR, to assist technicians in visualizing complex assemblies, ensuring accuracy during production. These automated systems are supported by digital tools like Spirit One, SAS, and Manufacturing Execution Systems, MES, which provide real-time data on production status, quality control, and supply chain coordination, enhancing operational efficiency across Spirit's global facilities in Wichita, Belfast, and Casablanca. In Friday, composite manufacturing is a hallmark of Spirit's technical expertise, driven by the aerospace industry's demand for lightweight, durable materials. Spirit excels in producing composite structures for aircraft, like the Boeing 787 Dreamliner and Airbus A220, which rely on carbon fiber reinforced polymers, CFRP, to reduce weight and improve fuel efficiency. In Kinston, North Carolina, Spirit manufactures composite fuselage sections for the 787, utilizing automated fiber placement (AFP) machines to lay down carbon fiber with precision. Similarly, its Belfast facility produces composite wings for the A220, employing resin transfer molding (RTM) to create strong, lightweight structures. These processes involve advanced curing techniques such as autoclave and out-of-autoclave methods to ensure material integrity under extreme conditions. Spirit's expertise in composites extends to defense applications, including lightweight fuselages for the Lockheed/Sikorsky CH-53K King Stallion, demonstrating its ability to meet stringent military specifications. Research and development are central to Spirit's technical innovation. The company collaborates with NASA's Advanced Composites Consortium to advance composite technologies for next-generation aircraft, focusing on high-rate production methods to meet increasing demand. Spirit's R&D efforts also explore ceramic matrix composites, CMCs, for hypersonic applications, which require materials capable of withstanding extreme temperatures. This work positions Spirit as a leader in defense manufacturing, particularly for programs like the Northrop Grumman B-21 Raider. Additionally, Spirit invests in additive manufacturing, 3D printing, to produce complex components with reduced lead times and material waste, further enhancing its production capabilities. Spirit's technical advancements are not without challenges. In 2024, production inefficiencies on the Boeing 787 and Airbus A220 programs led to a $217 million loss, partly due to complexities in composite manufacturing and supply chain disruptions. Quality control issues, such as the January 2024 Boeing 737 MAX 9-door plug incident, highlighted the need for rigorous process oversight. To address these, Spirit is enhancing its digital quality management systems, integrating AI to predict and mitigate production defects. The company's planned reintegration with Boeing, announced in July 2024, aims to streamline technical processes and improve quality assurance. Looking forward, Spirit's focus on automation, composites, and digital transformation positions it to meet the aerospace industry's evolving needs. Its investment in sustainable manufacturing, such as eco-friendly composites and energy-efficient processes, aligns with global trends toward greener aviation. By continuing to advance technologies like AI-driven manufacturing and hypersonic materials, Spirit AeroSystems remains a technical leader, driving innovation in aerostructure production for both commercial and defense applications. Later. The assembly of the YIZU MI8500T injection molding machine is a complex and precise operation. First, the massive components, including the platen weighing up to 140 tons, are carefully positioned in the factory space, covering about 251 square meters. Skilled technicians and engineers collaborate closely over 4 months. Robust structures like the tie bars, spaced 3,250 by 2,800 millimeters apart, are installed to support the machine's ultra-large size and high clamping force of 8,500 tons. Each part undergoes detailed fitting and alignment to ensure smooth operation. Throughout the process, advanced tools and machinery assist in handling heavy components safely. Heu!